Hello, everybody. Welcome to your final exam review. We are going to be doing this in two parts, and then you got to take your final exam, and I wish you good luck on it. So before we get into all the material, just going to, by the way, this is going over your study guide, so I hope you've printed out your study guide, and it'd be great if you could follow along and answer these questions as I go through it. So anyway, this is based off your study guide. You should see your study guide right up there. And before we get into all the material, I just want to go over kind of what... kind of the procedures for taking your exam here. Let me get my pen out. So remember that just like the midterm, you're taking this at the testing center. If you, for some reason, can't take it at the testing center, or maybe a lot of times people are working during 9 to 5 hours, I'm going to have two after hours times, one at Heritage, one at OSO. So stay tuned for that schedule to be released when I'm going to host and proctor exams. One time at the computer lab at Heritage, one time at the computer lab at OSO. Okay, so your test is worth about 200 points. It'll have about 100 questions, close to 100 questions, and it will be pretty close to 200 points, but plus or minus 10%. Usually is what I say. So anyway, you'll take that at the testing center, or you're going to take it with me at one of our computer labs. That testing center, I say you must take it between. I don't have a date, and that's because. It changes from semester to semester, but you must take it between just whatever it says on Canvas. So I use this video so multiple semesters, so I'm not going to tell you what the date is, but check Canvas to see when you should take the test. Testing center is open every day except for Sunday, so you should be able to take it on Saturday even. Those Saturday times fill up fast, so grab them when you still have a chance. You have to register at least 24 hours in advance for your test at the testing center. You register right here. Right? So do not procrastinate. Time slots fill up. And especially for the final exam, be really careful because we have very little time before the end of your last chance to take the final exam is like the day before final grades are due. So if you for some reason procrastinate and you don't find a slot and then you contact me on the day that final grades are due, it's going to be very unlikely I'm going to be able to accommodate you. Okay, so make sure that you get this taken care of way in advance. Do not procrastinate on this. We will have two walk-in times, like I said, that are after hours. So they're going to be probably in like the afternoon, like evening after work time. And we're going to do one at Coles 302 at Heritage Campus. And we're going to do another at OSO campus in the STEM building, room 339. This is a closed book, closed note test. There's no, collaboration, no notes, no books. You can have a piece of scratch paper, and that's a blank piece of scratch paper, and that's it. There's a mixture of different problem styles, open response. There's going to be at least four, maybe up to six short answer questions. You're going to have matching, multiple choice, true and false, ordering things, etc., etc., etc. Sometimes you'll have pictures. You have to say something about the picture or a graph or something like that. Okay, so that's your test. There's a practice test. Make sure you take the practice test. It's required. Plus, that's going to help prepare you for the test. Okay, I highly suggest, highly recommend doing flashcards for this. For this test, okay, as I do for all my tests. That's my recommendation. All right, so let's get into the material. We got a lot of stuff to cover. We're going to go through half of the study guide today, so up to about question number 65. That's why I need a drink of water, because I've got a lot of talking to do. So I hope you're ready. So let's go over, start metric system and scientific method. So true or false, can every question be answered by science? I do a whole lecture on this, and the answer is no. And that's, I don't think, an opinion either. The answer is no. Not every question could be answered by science, and I go over the reasons for that in that first lecture. So do you know the difference between a hypothesis and a prediction? Hypothesis is something that seeks to explain how nature works. Okay? How nature works. And a prediction is really kind of totally unrelated. It's just funny that people get them confused a lot. So a hypothesis explains how nature works. So for example, the one that I gave in the lecture is, why do the leaves fall off the trees at winter time or in fall time? It's because our hypothesis does, it's because the temperatures get cold, or because the time change, right? The lessened amount of daylight, right? We're trying to put forth a hypothesis about how nature works, okay? An explanation. We're trying to explain. Prediction doesn't do that. A prediction is just a guess about what is going to happen. So it's a guess about a future observation. Okay, that's all there is to it. Possible short answer questions. So pay attention to these. You're going to see these as we move through the lecture material. So this is giving you a hint at this could possibly be one of your short answer questions. Basically, the way your test works is there's a question bank. And actually, as a matter of fact, every question on this study guide that you see right up here, this study guide, it's going to be on the question bank, and you're going to get a random selection of those questions from the question bank. Everybody's different, and that's for test security, to make sure that everybody gets a slightly different test. But you know all of the questions. They're given to you right now. This is going to be a possible short answer. So what are some of the necessary criteria for a question to qualify as a valid scientific question? So remember that not every question is a scientific question. Some things can't be answered by science. What kind of questions can be answered by science? There are three things that we talk about in this lecture. Number one is it has to be falsifiable. It has to be falsifiable. What does falsifiable means? It means that you can verify or refute the claim by scientific evidence, or by physical, maybe I should say more clearly, by physical observation. So you can verify or falsify by evidence. Okay? Evidence means something very distinct here. It's evidence is an observation, okay? It's distinct from reason and from logic, okay? It's something that you can actually see and verify with your eyes, with your ears, with your senses. It's an empirical observation, okay? Also, I'm gonna give myself a little bit more room to write things here. Let me kind of space this out a little bit more. Look at how much stuff we got to go through, boy. Well, gird your loins and get ready for it. So we can probably go up to. We can probably stop here when we get to metamorphic rocks here. Whoops. Okay. Let me space this out a little bit so I have more room to write and explain this stuff. So we're going to go to layout, paragraphs, and I'm going to add like 48 here, like that. All right. So what's another thing? Pardon me. I'm kind of just getting over a sickness, so I'm sorry if I'm coughing or something. But also remember, things have to be reproducible. Okay? What does reproducible mean? It means that anybody can come along and reproduce your experimental results or your observations. So people have to be able to observe the same observation that you made to verify or falsify your hypothesis or your scientific claim. Okay? So that's the next thing. The last thing is that it has to be something physical and observable. And that's kind of really tied up with the last two criteria that I talked about, right? There has to be something physical and observable. If it's not something that is you can see, for example, we don't do scientific studies on, for example, people's emotions or on their logic or thinking or philosophy or philosophical questions or things like this, because those are all abstract ideas. They're not things that can be physically seen or observed, right? We don't do scientific experiments on certain political ideologies or something like that, because we can't see and observe those things. They're ideas, right? So it has to be something that's physical and observable. Do not be surprised if on the test I ask you to come up with an example of a question or something that cannot be scientifically studied. Okay, so that's something that you're already familiar with. I had that in lecture assignments, so just be prepared for something like that. All right, you should also know the base metric system units for space, time, volume, mass. So this is going back to the metric system. So, for space, for distances, we use meters. For time, we use seconds. right? For volume, we use, and of course, volume is just a distance by a distance by a distance, right? We use, so that's one of those, remember, independent versus dependent measurements, dimensions, I should say. Volume, we use liters. Sometimes we use cubic centimeters if it's a small thing. Mass, we use, for mass, we use kilograms, okay? So you should know also prefixes, mega, kilo, centi, and milli. So remember how the prefixes work in the metric system. You have your base unit, okay, that's times 1, okay? That's your base unit. Then you have, if you want to scale it up by tens, right? So by 10, by 100, by 1,000. And we can also put up here by 1 million. Okay, I'm going to put 1 million up here. That's mega up here, 1 million. So, you know, a mega meter has 1 million meters in it. Okay, going down this list, kilo is 1,000. So a kilometer, a kilometer, has 1,000 meters in it. Okay, next one is a hecta, right? Hecta is 100, so a hecameter has 100 meters in it. A decameter has 10 meters in it. Okay, 1 decameter is 10 meters, so it's about 100 feet. Okay, so that's how it works when you're scaling up. Now you can also scale down. So the base, we can scale it down. We have a deci, and that's times 1/10. So 1/10 of a meter is a decimeter. So there's 10 decimeters in a meter. You can also have a centa. Okay, centimeter. That's 1/100th. Okay, times 1/100th. That's 100 centimeters in a meter. 1/100th of a meter. We can also have milli. That's times 1/1000. So that means there's 1,000 millimeters in a meter. And notice that as you go up, this goes up by tens, right? So 10 millimeters in a centimeter, 10 centimeters in a decimeter, 10 decimeters in a meter, a base unit, right? So that's how it all works. And remember, when you want to go from, for example, from a millimeter to a megameter, you have to count the jumps that you do, right? So you would go to 1, 2, 3, 4, 5, 6, and then here we actually do, you might notice we actually do 3 jumps right here. So that would be 9. So there's 1 billion millimeters in a megameter, for example. Bet you didn't know that. So anyway, be prepared, because there's going to be multiple questions on there that'll ask you something like, how many meters in a kilometer? How many centimeters in a meter? Et cetera, et cetera, et cetera. Okay, so be prepared. Make sure that you can convert between everything that I wrote down right here. Okay, I'm not going to go into things like nanometers or micrometers or gigameters or things like that. Okay, just the prefixes I have right here, right up there. Okay, so be prepared. Pardon me, sorry. All right, you should also be able to answer questions like how many, okay, well that's just what I just talked about. Okay, so we just covered that. You might have to convert in a simple way between English system units. So I want you to have some grasp of how English units convert to metric system units, okay? You will not have any question that requires a calculator, all right? It's just going to be something fairly simple, like ballpark estimates. So for example, but it would be good to know just these 4 things here. How many inches are there in a centimeter, or rather centimeters to inches? So they're 2.54 centimeters per inch. Okay. There are 3.28 feet per meter. There are 2.2 pounds per kilogram. And they're 1.6 kilometers per mile. So I just want you to have like a very basic idea of how English system units, common English system units, compare to common metric system units. You're not going to have to do any like really rigorous conversions, but like for example, the way this will go is it'll be like this: like 10 inches is roughly equivalent to, and then you'll have like the correct answer, 25.4 centimeters. 10 inches is roughly equivalent to 25.4 centimeters, right? 2.54 centimeters per inch. B, 1,000 centimeters. C, 0.1 centimeter, something like that, right? Things that are totally way off. I just want you to have some gut intuition about how English system units compare to metric system units, okay? All right, so going on to global geography, what's the special name given to the 0-degree meridian? That's the prime meridian. Okay. Do those meridians intersect? They certainly do. Remember that meridians all intersect at pole to pole. So they're kind of like those lines on a watermelon or a cantaloupe that go from stem end to blossom end. So meridian lines go from the top, the North Pole, to the bottom, South Pole, and they all connect and they all intersect at the poles. Do parallels intersect, though? And the answer to that is no. Remember that parallels go straight across. They are actually circles that completely go around the Earth at different latitudes, right? So do parallels intersect? No, right? Which parallel is furthest from the poles? The parallel that's furthest from the poles, so here are the poles up here, right? North and south. The parallel that's furthest from the poles is the equator, right? So this would be the equator. And the one that is closest to the poles, I don't ask that, so that's good. That's kind of a confusing question. But the one that's closest to the poles would be the poles themselves, which are lines of latitude. Okay, they're parallel. So that's 90 degrees north, 90 degrees south. Okay, remember that parallels can only go up to 90 degrees, whereas meridians can go up all the way to 180. Okay, 180 north, 180 east, 180 west. Okay, pardon me, sorry, I'm congested. Which parallel is furthest from the poles? Where I asked that. Okay, that's the equator. What's the climate like at high latitudes, 75 degrees north, 75 degrees south? The reason I put south here is because a lot of people just automatically think, oh, it's south, it's hot. Well, only in the northern hemisphere is that true. So it's actually cold at 75 degrees south because it's in the polar, or I should say Antarctic circle, right? The climate around 10 degrees north, what is that like? Well, it's the opposite. It's rather hot and tropical, right? Remember, anything within 23.5 degrees north, 23.5 degrees south, anything within those lines, those are the tropic lines, it's going to be warm and tropical. All right, so moving on. Remember that those tropic lines are not just arbitrary lines. They are connected to the tilt of the rotational axis of Earth. So here's our orbital plane. There's Earth, and you know that our axis is about 23.5 degrees off kilter from a perfect perpendicular in relativity to that orbital plane. So 23.5, that's a magic number. Make sure you know that number. Okay, that's coming up. And it comes up in a lot of different ways, so make sure you know 23.5 degrees. That's the tilt of our rotational axis. All right, you could have a map like this, and I could ask you where some different features are. So the way that this would work is I would have something like, A, B, C. Where are the Andes Mountains? Well, it would be at B. So that's how that question would go. Okay. So just make sure you have a basic grasp of where these different geographical features are that we have covered in our class. So the Aleutian Islands are right here. I'm going to put A for Aleutian Islands. Japan is right here. I'll put J for Japan. The Andes Mountains here, I'll put AN for Andes, A and D for Andes. The Himalayas are right here at north of India. Okay. The Appalachians are over here. Okay, I'll put APP for Appalachians. Rocky Mountains are here. I'll put R for Rocky. Gulf of Mexico, hope you all know where that is. That's right here, Gulf of Mexico. Hudson Bay is right up here. Okay, and then Greenland is this island right there. That's Greenland. Iceland is this island right there. Sumatra is this island right here. And the Philippines is right here. And Lake Baikal is right here. I'll put Baikal. Okay. And then the Sahara Desert is there in North Africa. The Atacama Desert here. I'll put this Atacama right next. It actually goes alongside the Andes Mountains. Okay. So just make sure you know where all those structures are. Okay. How old is the Earth? It is 4.5 billion years old according to radiometric dating done by the scientists. Okay. So that's how old it is, we think, from radiometric dating in terms of when it accreted together. Okay. What are the four basic layers or spheres of the Earth? The four basic layers or spheres are the inner core, right? The outer core, the mantle, and the crust. I can't even draw the crust on here because the crust is so thin. Okay. Which of those 4 layers are molten? It's the outer core only. The mantle is not molten. I hope that I've impressed that upon you enough times by now that it's second nature. Okay, 4 most abundant elements in the whole Earth. So in the whole Earth, it's actually our first one is iron, oxygen, magnesium, and silicon. Now, when you consider just the crust is going to be very similar, but it's going to be a little bit off. So it's oxygen, silicon. Instead of magnesium, we're going to have aluminum and iron. Okay, so make sure you get those 2 kind of straightened out in your head because they're similar, but those are 2 different questions. Be careful on the test. Make sure that you notice, is it asking for the whole Earth or just for the crust? All right, now what is the MOHO? The MOHO is just the boundary between, let's say, the crust. Here's the crust. Here's ocean crust. So this is going to be continental crust. This will be ocean crust, and the mantle. Okay, so this line right here would be the MOHO. All right, the Mohorovicic discontinuity. All right, what's the composition of the core? What is it made of, and how do we know that? So the composition of the core is an iron-nickel alloy, and it's about, maybe 90% iron. It's maybe about 5% nickel, and it's 5% other stuff. Mostly you want to know, though, it's iron, okay? It's molten iron in the outer core. It's solid iron in the inner core. So how do we know that? We know that from seismic velocities and seismic waves and seismic analysis. When there's an earthquake on the surface of the Earth, so let's say there's an earthquake right here, it sends down waves into to the interior of the Earth. It's big enough, Earth, especially a big earthquake's big enough to shake the whole Earth. So those seismic waves propagate through the mantle and they hit the core. S waves do not go through the core, they bounce off of the core. But P waves, I'm going to draw P waves in a different way. P waves actually do go through the core, the outer core and the inner core. So that's how we know. It's actually whether it's an S wave or a P wave tells us a lot about what the composition of the interior of the mantle is, or interior of the Earth is, sorry. All right, what proportion of Earth's mass is in the mantle? It is about 66%. The crust is very small, only 0.6%, and the core is about 33%. Okay, so it is 2/3 rock, mantle is rock, 1/3 metal, and then just a little tiny little sprinkling of crust on top, okay? But it's 2/3 rock, 1/3 metal. Pardon me again. I'm sorry. It must be so unpleasant for you to hear me coughing, but I gotta do it. Hey, you know what? I have a cough drop. I should take a cough drop. Oh, but cough drops taste terrible with coffee. What am I gonna do? It's all right. All right. So, how is Earth's magnetic field generated? It is generated by convection. Convection in the outer core. So, here's Earth. Here's the outer core here. Here's the inner core. And, the outer core is a liquid, and it's convecting, and it's moving. And that circulation of a ferromagnesian mineral, ferromagnesian material, I should say, creates an electrical current, which creates, in turn, a magnetic field. And that is what generates that beautiful magnetic field that we need to deflect any nasty solar winds and things like that come from the sun that would otherwise obliterate life on Earth. Okay, so what's the primary difference between mantle asthenosphere and mantle lithosphere? The primary difference, it's a mechanical difference, okay? It's a mechanical difference. So you've got to be careful with this because there are a lot of differences between the asthenosphere and the lithosphere, right? There are a lot of differences between them. The asthenosphere, for instance, is lower, it's deeper in the Earth than the lithosphere. That's true. The asthenosphere is also warmer than the lithosphere. That's true too. But those aren't the primary differences. They're just sort of accidental differences. The primary difference is that there's a mechanical difference in how it behaves. So asthenosphere is warm, pliable, malleable. It folds, it moves, and it convects. so it's a mechanical difference. This has convection, okay? Whereas the lithosphere has no convection, and it is kind of more like a typical rock that you would think of. You know, it's stiff, it's cold, it's breaks, it's brittle, it's not going to move around, and et cetera, et cetera, et cetera. Okay, so that's the difference, a mechanical difference. All right, now what are some of the differences between continental crust and ocean crust? This is a short answer question. So average density of ocean crust is it's denser, okay? And it's about 3.0 grams per cc. This over here is about 2.7 grams per cc. For average thickness, you have a thickness here in the ocean crust of only about 5 to 7 kilometers. Over here about 30 kilometers, up to 70 kilometers. Okay. Average age. The age of the seafloor is pretty young. It's less than 180 million years, whereas the age of the continental crust pretty old, maybe 2.5 GA on average, less than 4 GA. GA is billion years. Okay, so 2.3 billion years. Average rock type. Remember, this is mafic, so it's basalt. Over here is diorite. Composition is mafic for the ocean crust, intermediate for the continental crust. Average elevation is obvious. This is negative 4 kilometers. That means 4 kilometers below sea level. Over here, it's about 0.5 kilometers above sea level. Okay, so that's that. Moving on to minerals and matter. So what are those 3 subatomic particles? You know that we have a nucleus with protons and neutrons, right? Protons are plus charge, neutrons are neutral charge. And of course, around the nucleus, we have these shells of electrons, right? And electrons have a negative charge on them. Electrons are very small. They're only about 1/10,000th of the mass of a proton, okay? So the protons are much larger than electrons. So for example, something that's like 10,000 times larger than you, right? If you weigh 100 kilograms, you're talking about something that would be a million kilograms, right? That's something much many. You know, it's almost like comparing your body to a house or something like that, right? Or to a building. So that's how an electron compares to a proton. All right. So where is the vast majority of an atom's mass concentrated? Concentrated in the nucleus, by far in the nucleus. Okay. So what is an ion? What are the differences between ionic, covalent, metallic bonds? Don't worry about metallic. I don't know why I put metallic there. I don't even talk about metallic bonds in this class. That's a kind of mistake. But an ion is an atom with a net charge, right? So it has a net charge. What does a net charge mean? So that means that it either has a plus or negative charge. Okay, non-zero charge. What's the difference between ionic, covalent bonds? So ionic bonds are involved between 2 ions, and it involves near total transfer of electrons. So remember, there's like one gives electrons, another receives electrons to complete that octet rule. Remember the octet rule where you want to try to get 8 electrons totally fill up your outer shells. Of course, you know, in the first shell you can only hold 2 electrons, but in subsequent shells you can hold 8. For covalent bonds, we have, instead of giving and taking, we have sharing, right? So we have sharing of electrons to complete that octet rule, okay, and make the atoms happy. You should be able to draw a picture of a silicate molecule. You will not have to draw one on the test, but you will have to recognize one. So the way that works is I'll have like a lineup of possible suspects, and you have to pick out the silicate molecule. Remember that silicate molecule has one silicon atom in the center, surrounded by 4 oxygens. Okay, like that. That kind of looks superficially like a pyramid shape, but it's actually not a pyramid. It's a tetrahedron. Means that it has 4 faces, not 5. Pyramids have 5 faces. Tetrahedron only have 4. All right, what's the ionic charge on it? Total charge on this silicate tetrahedron is -4. That's because there's a -2 for every oxygen, and there's a +4 for the silicon in the center. If you do all the addition, it adds up to -4. What are 4 common elements in the crust? I already talked about that. It is, or I should say they are, iron, oxygen, silicon, and aluminum. What are the 6 very common, sorry, I'm getting all tongue-tied here, 6 very common groups of rock-forming silicate minerals, okay? I talked about these ones a lot. You should definitely know them. They're part of Bowen's reaction series. So we have olivine, pyroxene, amphibole, mica, feldspar, and quartz. Okay. What are the 5 silicate structures of the above minerals? Okay. So for olivine, it is it's that isolated structure. Okay. Remember, that's when the silicate tetrahedra are just by themselves. Okay, they're not connected. For pyroxene, single chain. Single chain means that the tetrahedra are connected like that. Where every tetrahedra is sharing with 2 others. So it's tetrahedra have 4 oxygens to share. A single chain is sharing 2 of the 4. So basically half the oxygens are what we call bridging oxygens. Amphibole. Amphibole are called double chain. Double chain is when you have basically 2 single chains that are connected together. So you could imagine these things be connected together, and what happens in that case is that every other tetrahedron has 2 sharing oxygens, and every other tetrahedron has 3 sharing oxygens. So on average, there are, I could say, 2.5 shared oxygens per tetrahedron. For mica, there are 3 shared oxygens per tetrahedron, so 3 out of the 4 are shared. So they have a sheet silicate structure. For the feldspar and quartz, they have the tectosilicate framework, aka the framework structure, and that is where it's a 3-dimensional framework. I can't draw it. You won't be expected. I won't expect you to recognize that by sight, because it's hard because it's 3-dimensional. But anyway, well, maybe I retract that statement. It might be on your test. I can't remember, but it's 3-dimensional, so it's hard for me to draw it up here. I have to try to draw 3D. But anyway, feldspar and quartz. Just remember that their tecto framework silicates every single oxygen on the tetrahedra are bridging oxygen. That means that they're connected somehow. Okay, so you should be able to recognize these by sight, because I'm going to have pictures of some of these silicate structures. You have to recognize by sight. Recognize which silicate structure it is. Is it isolated? Is it single chain? Is it double chain? Is it sheet silicate? Is it tectosilicate? Okay, so be prepared for that. Go back to the lectures and look at that and make sure that you can recognize them. All right, what are some of the physical characteristics of minerals? We talked about 8 of them in class. So, and you should have some basic understanding of these. Be able to explain each one of these with like one sentence. So those are hardness, color. Color is pretty easy to explain. Streak. Hardness is the ability of a mineral to scratch. Okay. Color is just which wavelengths of light are absorbed by the rock's surface, mineral surface. Streak is the color of the pulverized mineral. Luster is how light reflects off of the surface of the mineral. We also have cleavage. Cleavage is there a pattern to breakage in the mineral? Okay, or they're cleavage planes, right? And sometimes you can have multiple cleavage planes in a mineral. Sometimes you have no cleavage in a mineral, okay? But it's a pattern to the breakage in the mineral. You can have specific gravity, aka density, right? That's the how much mass there is per unit volume. You can also have special properties, such as magnetism, like magnetite. You can have salty taste for halite. You can have reaction with acid for calcite, things like that. Got special unique properties. I'm missing one. What is it? It'll come back to me later, probably. Crystal habit. So crystal habit is how the crystals look, how the form, the shape of the crystals when crystals do form from the mineral. Okay, so some minerals have very special crystal habits, very special shapes to the minerals that are very, very characteristic. All right, what are minerals? What are those 5 criteria? The 5 criteria being a mineral are solid, I can say geologic, formed by a geologic process, not a biologic process. Also, you have to be I'm forgetting this stuff, aren't I? You have to be crystal. Whoops. You have to have a crystal form or crystal lattice. Okay, so a highly ordered interior, atomic interior. You have to also be definable with a chemical formula, definable chemical formula. And last but not least, you have to be naturally made. Okay, so no synthetic minerals. All right. Okay, so moving along, what is the most common silicate mineral of the crust? In that case, it is feldspar. What about non-silicate mineral? It's probably calcite. Okay. So most common minerals are silicate minerals in the crust, but there are some non-silicate minerals like calcite, which is a carbonate mineral, and you should be familiar with both of those. So calcite, a silicate or non-silicate, is a non-silicate. Okay, it's a carbonate mineral. All right, going on to igneous rocks. What are the 3 basic rock types? So make sure you know it's igneous, metamorphic, and sedimentary. Almost everybody gets that one right, actually. Very few people get that one wrong. What defines an igneous rock? An igneous rock is formed from a melt. Okay, that's the important thing. It was at some point melt. It was liquid, and then it solidified. Okay, it crystallized, and didn't necessarily cool, but it crystallized. Okay, so it became solid from a melt. Plutonic igneous rocks. What are plutonic igneous rocks? They are things that form from a magma. They form from underground. They cool underground, crystallize underground. Okay, they never reach the surface. Some common plutonic rocks are granite, gabbro, diorite, etc., etc. Okay, what's a common rock with a glassy texture? That's obsidian. Okay, it's a volcanic rock that cools very quickly. It cools so fast there are no crystals. There's only glass. Glass is different than a crystal because glass has a liquid structure, even though it is solid. Okay, but it has a liquid atomic structure. In an igneous rock, what's the difference between a coarse grain texture and a fine grain texture? So coarse grain texture means that it's equivalent to plutonic rocks. So plutonic rocks have a coarse grain texture. So when all of the crystals are visible, you can see them. So another term for that we use is phaneritic. For fine grain, it means that the crystals are not visible. That means we call that aphanitic. Aphanitic means you can't see the individual crystals. They're too small to actually see. Be able to recognize this in a picture. So if I were you, I'd just get some pictures on Google Images of basalt and granite and just make sure that you can look at the texture like that and say, okay, this is a coarse-grained phaneritic rock. This is an aphanitic fine-grained rock, okay? All right, so most rock-forming minerals are built up out of silicate molecules. Notable exception to this is calcite, which is, like I said before, carbonate. Okay. you should be able to fill out this table with the correct igneous rock types. So, so here a felsic fine-grained rock is a rhyolite. Intermediate fine-grained rock is andesite. The mafic one is basalt. For a felsic coarse-grained rock is granite. An intermediate coarse-grained rock is diorite. And a mafic coarse-grained rock is called a gabbro. Okay, so make sure that you can fill out that table. The way that it'll look in your test is, you know, you'll have it numbered like that, 1, 2, 3, 4, 5, and also say, you know, what goes number 4, what goes to number 5, what goes to number 6, etc., etc. Okay, so be prepared for that. What are some specific differences between composition of felsic and mafic rocks? Okay, so which elements are less abundant or more abundant? Okay, so I'm asking about elements. So remember that felsic and mafic are compositional terms. It tells you what the rock is made of in terms of elements and atoms. Okay, for a mafic rock, we have mafic. We have less SiO2. So just about maybe 50% SiO2. And we have more magnesium and iron. For a felsic, we have more SiO2, maybe about 75%. And we have more potassium and so we have more potassium, more sodium. Okay, those are the main differences there. All right, you should know the difference between the continuous and discontinuous Bowen's reaction series. Maybe that the Bowen's reaction series, we have kind of like two parts of it. Discontinuous is that series of different minerals, olivine, pyroxene, amphibole, and then we have mica, quartz, feldspar. Okay, and then on the continuous, that's discontinuous. The continuous series, we're going to have just plage, and that plage is going to go from calcium rich down to sodium rich, from going from a high temp to a low temperature. So remember that Bowen's reaction series is all about if you had a mafic melt slowly cooling, which crystals are crystallizing out, which minerals are crystallizing out in accordance with the temperature. Okay, high temperature, you're going to have olivine and pyroxene, more like the mafic minerals. You're going to have calcium-rich plagioclase. As things cool down, you start to precipitate out things that are more felsic, so things like mica, quartz, feldspar, and sodium-rich plagioclase. All right, so moving on, you should know the series of minerals from high temp to low temp that precipitate from a cooling magma under the discontinuous series. So again, that's olivine, pyroxene, amphibole, mica, quartz, and feldspar and quartz. I should say orthoclase, potassium, feldspar, and quartz. For the continuous series, make sure you know how the composition of plagioclase changes from high temperature to low temperature. It's simple. It just goes from calcium-rich to sodium-rich. Okay, calcium-rich is at high temperature. Sodium-rich is at low temperature. All right, so moving along, going now from rocks and minerals, moving to geomorphology. We're going to start talking about weather here. Oh, actually, I shouldn't say moving away from rocks because we still have to cover sedimentary rocks. This is more of the sedimentary rock series. All right, so first of all, you should know, what is weathering? Weathering, very simply, is just a process that breaks down the rock into small pieces. Okay, and those small pieces are called clasts. What are the two main categories of weathering? Okay, there's physical. Whoops. Here we go. Physical and chemical. So you should be prepared because you could have a short answer question about this that says, describe with a sentence one physical weathering process, one chemical weathering process. You might also have to explain the difference between chemical weathering and physical weathering. Physical/mechanical weathering means that you break down the rock with no chemical change. So no chemical reaction. Okay, no reaction. Chemical weathering is just the opposite. You break down the rock with chemical reactions. You change the chemistry. You change the composition. So what's a chemical weathering process? An example of chemical weathering process, example of a physical weathering process. We talked about a lot of them in lecture. Physical weathering, what did we talk about? We talked about frost wedging. So here's physical, mechanical. Okay, like that. We had talked about frost wedging, talked about jointing, talked about exfoliation domes. We also talked about things like salt wedging, talked about thermal expansion. Okay, a lot of different things we talked about. I don't want to go through each of these and explain each of these again, but go back to that lecture and listen again. Make sure that coming into this test, you can explain one of these. Explain with just a sentence. Frost wedging or whatever. Make sure that you can explain the process of frost wedging. Like, okay, water seeps into cracks in the rocks, it freezes, it expands, and it breaks the rock apart. It's enough said. Chemical weathering. Talked about oxidation. What is oxidation? The oxygen in the water reacts with iron minerals in the rock. Okay, that's all you have to say. Oxidation, hydrolysis, and carbonation. So again, make sure you know what all those things are. I can't explain everything here. I'm already 45 minutes. I got still about 10 more questions to talk about, so I don't want to go in explaining everything. But go back to the lecture and listen. Make sure that you can explain at least one of those processes. Pardon me. Sorry. How can water weather rocks? Well, look at a lot of these processes we just talked about involve water. All the chemical weathering processes involve water. Oxidation, hydrolysis, carbonation, they all involve water. Frost wedging involves water. A lot of the biological processes of weathering require water, right? Just because life requires water. So just make sure that you have that connected in your mind, that water really causes a lot of weathering on rocks. And I'm sure you know that. Like if you want something to last, you don't leave it out exposed to the rain, right? Because the rain, your bicycle, you don't leave your bicycle exposed to the rain because it just weather it away. You don't leave a chainsaw or a power tool or something out in the rain because it will get weathered away and destroyed, right? So I just want you to make sure you know some specific processes that are connected with weathering and with water. Okay, specific weathering processes that are connected to water. Some biological activities that contribute to weathering. Big one that's obvious is root wedging, right? When the roots get in between the cracks of rocks, they break the rocks apart. Another thing, though, you might know about are lichens. Lichens are kind of like rock mold. They are actually a symbiotic combination of two organisms. There's a fungus and an algae that grow together, and they provide different things to each other, and they're able to break down the rock with organic acids. Now, what's produced by the reaction of water with feldspar and granite? So what's produced is clay and quartz. Mostly clay, though. Clay is really what I want you to know. Okay, clay minerals are produced when feldspar breaks down. What compounds produce when CO2 from the air dissolves into water? CO2 plus H2O gives you can actually just add up all of the elements there. You get H2CO3, and that is carbonic acid. Okay, so carbonic acid is created in the water. How does that change the pH of the water? The way that changes the pH is that it lowers it, makes it more acid, more acidic. What mineral is easily weathered by acidic water? Calcite. And a lot of limestone is composed mostly of calcite. So that means that limestone gets eaten away very easily by carbonation, reaction with carbonic acid, which is called carbonation. It breaks down the rock. All right, going on to sedimentary rocks. What are those four categories of sedimentary rocks that we've talked about? Well, we talked about chemical, biochemical, and clastic, and organic. Okay, make sure that there's a list of rocks. I think I talk about it later. Let me just make sure. Yeah, so we're going to talk about all these things in a minute. But so chemical, biochemical, clastic, organic. What's a chemical rock? It's made out of the precipitated PPT. PPT means precipitated chemical grains out of water. So some mineral material precipitates out of the water. Anyone who likes to boil water in a tea kettle has probably seen little bits of mineral grains that get precipitated at the bottom of your tea kettle. Maybe a lot of you are familiar with hard water buildup around your maybe like your pipes or around your bathtub or something like that. That's all precipitated mineral material. It happens naturally as well as in your home. Okay, so that would form over years. Imagine what your bathtub would look like after 1,000,000 years if you didn't clean it, right? It would have all this hard water buildup. It would be a rock, right? It's a chemical rock. Biochemical is formed from shells and tests of microorganisms in the ocean, marine microorganisms. I can say also macroorganisms as well, like clams and oysters and things, but mostly it's microorganisms. Clastic rocks are the bits of broken rock and mineral that are broken from the bedrock, and like sand, shale, clays, things like that conglomerate together to form a clastic sedimentary rock. Organic rocks are made of organic matter. The only example I really give of that in this class is coal. I guess you could also say oil shale a little bit as well. So clastic sedimentary rocks are classified on the basis of, so how do we classify different clastic sedimentary rocks? We classify on the basis of grain size. Okay, small grain size such as shale made from clay grains. Okay, we call that a shale. If it's made from silt, we call it a siltstone. If it's made from sand, we call it a sandstone. If it's made from pebbles or things like that, we call it a conglomerate or a breccia. What are some things that can be sediment of a sedimentary rock? These are kind of connected to the categories of sedimentary rock. So we could have precipitated grains, right? That's a chemical. We can have shells and tests. That's biochemical. We can have mineral rock grains. Sorry, I'm misspelling everything. That would be clastic. And we could have organic matter. And guess what? That would be organic. Okay, so I just want you to be aware of the sorts of things, there's 4 of them, that can be the sediment of the sedimentary rock. Okay, for the following sedimentary rocks, you should know their category, depositional environment, and you should know the chemical composition, dominant mineral, for some of the ones that have an asterisk next to them. So a conglomerate and a breccia, those are clastic. Okay, conglomerates form either in glacial environments or fluvial. That means a river. Fluvial. Breccias form from debris slides, like landslides. What's the difference between breccia and conglomerate? Breccia is more like angular grains, like this. Okay, so the breccia is composed of angular grains, whereas the conglomerate has more like well-rounded grains. Okay, so there's your conglomerate rock. There's your breccia rock. Okay. Now, sandstone can form in a beach environment, but also in deserts. It's clastic. Siltstones form in deltas, back bays, and also in like estuaries. And it's also clastic. Shales form in shallow marine or delta environments. Along with the same things with siltstone. It can be in back bays and estuaries as well. Rock salt forms in desert environments. Remember when we talked about the desert lecture, we talked about playas and the formation of playas. Playas are like lakes, inland lakes in the desert that evaporate, constantly evaporate. They fill up, they evaporate. They fill up and evaporate with every rain shower. And as they evaporate, they build up rock salt and things like that. Okay, so gypsum and rock salt both form in desert, inland lake environments. Coal forms in a swamp, usually a coastal swamp. Like think of Louisiana or Alabama, something like that. Limestone forms in marine environments. Okay, a reef, especially like reefs, like coral reefs, things like that. Chert is a deep water, deep marine environment. All right, a possible short answer question. Describe a clastic sedimentary rock which the class have come from far away, have experienced loss of transport. Discuss chemical maturity, rounding, sorting, the size of the class. So with a classic sedimentary rock that has experienced a lot of transport, the chemical grains are going to be chemically mature. That means they're going to consist mostly of quartz and clay. They're not going to have things like olivine or amphibole that get weathered really easily. Not going to have any calcite or halite. Those things get weathered too easily. When it gets transported from far away, it breaks down. As it breaks down, those things that are chemically susceptible to chemical weathering, those minerals just break down and are destroyed. And they leave quartz, clay, hematite, things that are the products of chemical weathering that don't break down so easily. Okay. We also have rounding. Things are going to be well-rounded. The more that they're transported, the more well-rounded they're going to be. We're also going to have well-sorted. The more transport, the better the sorting. And the size is going to be small, right? You're going to have maybe sand, silt, clay, shale, siltstones, sandstones, fine-grained sandstones. That's what a lot of transport's going to do, okay? So be prepared for a question like that. And you know what? Make sure that you can answer the opposite, because I might switch it up on you and ask you, like, what is a rock going to be like that has experienced very little transport? It's close to source. Can you answer that? So just to switch everything around, right? It's going to be angular grains, poorly sorted. It's going to have large chunks, going to be more like a conglomerate or a breccia. Okay, it's going to have a lot of junk in it. It's not going to be chemically mature. It's going to be chemically immature. It's going to have olivine or amphibole or micas or things like that should have broken down a long time ago. All right, the final section we're going to talk about today, and I'll be done for this time, stratigraphy. Make sure you can recognize different unconformities, right? You should be able to recognize from a picture, be able to recognize an angular unconformity, be able to recognize a nonconformity. What is an unconformity? An unconformity is when there's missing time in the depositional record. And that means that deposition has stopped for a time and resumes later. The way that you recognize that is either from an angular unconformity, a nonconformity, or a disconformity. I cannot give you a picture of a disconformity because you could never recognize it. You know, you would have to be in the field. Even an experienced geologist might have trouble recognizing a disconformity. We can recognize, however, angular unconformity. So be prepared for a picture and recognizing that in a picture form. A nonconformity too, because remember that nonconformity, you have granite or gneiss or some kind of metamorphic rock, and you have layers sitting on top of the metamorphic rock. Okay. So given a geological cross-section like the one shown below, you should be able to put the various geological events in order. So note some of on the test be significantly simpler than this one. So on the test, this is a really complicated one. I would not expect you to be able to, if you can do this, great. But the one on the test is going to be much simpler. So this one's very complicated, but it gives you something to chew on. So personally, I find it easiest to work backwards, starting with the youngest event, the most recent event, and working back. So looking at this, it looks to me like the most recent event to have occurred is S. Okay, I'm going to put S here because you can see that S is cutting into J, right? You see how S has cut into J. So I'm kind of thinking that J, and I guess you could put N. N is kind of the unconformity that exists right there, which would be a disconformity. And you could put J after that. Okay. Now notice J, there's the Z here is a disconformity. Okay. Z is a disconformity because there's definitely missing time between this D layer and this J layer. Okay. So I'm going to put Z right here. All right, notice that this fault K is cut by J, and we also see that the tilting here, the tilted layers are also cut by J, layer J. So, but I want to point something out. K, the fault K, cuts X, right? So K, the fault, had to come after the tilting event and it had to come after deposition of X, and et cetera, et cetera. So I'm going to put the next thing is K, the fault. That's from cross-cutting relationships. After that, I'm going to put some kind of, there's tilting after that. Or I should say right before the faulting, there was tilting. Okay. And then we have deposition of X, deposition of E. And then a lot of crazy stuff happened before that. We see that there was implantation of a dike or intrusion of a dike. There was folding. Okay, you can see the folded rock layers here. A, H, R, B. Okay. What came first? Well, what came first was the folding, because you could see the folded rock layers are cut by the dike M. So I'm going to say M came right before that, and then right before that we had some kind of folding event. Okay, and then after that, right before that we have A, H, R, B. You can see that right here, this is a granite layer, and there's these inclusions here. That means that this is a nonconformity. It's a nonconformity. This up here is a disconformity. This right here is a angular. And then, that's an angular unconformity. Okay. So then B, there was this unconformity event. Let's see. It's kind of hard to tell. The remaining things we have are F, P. Okay, we could put C. That's the unconformity or nonconformity. C is right here. That's the nonconformity. We have G. G obviously came after P, and P came after F. How do I know that? G cuts P. Okay, so I'm going to put G here. I'm going to put P here. I'm going to put F here. Okay, G cuts P. P has an inclusion of F, which means F had to exist before P. Okay, so it appears to me that the oldest layer here, the oldest thing here is F. So I think I solved everything. But anyway, there's an angular O here. This is an angular unconformity. So O equals angular unconformity. All right, now I know that was like, I hope you're not like thinking, like, oh my goodness, I could never do that. And that's okay. That's a really hard one. That was a little challenging even for me. So you are not going to have one that hard on the test, but you have to be able to do something kind of like that with maybe only 4 or 5 or 6 events. Okay. I think that there's 2 of them on the test. One of them has only like 4 events. Okay. So it's pretty easy to kind of figure out which event happened. This one had how many? There were like a gazillion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different events. That's really hard. But anyway, that's all I have for you right now. So I'm all done, and I just want to say tune in for the next part. Don't skip the next part. Some people watch the first part, they don't watch the second part. Well, that's half the test. Okay, so second part will be coming soon. Anyway, make your flashcards, study hard, and good luck on the test. Okay, and let me know if you have any questions. Okay, because I'm here to help you succeed in the class. See you next time.